Okay, here we start with a functions, sine functions, and x. Okay, now we know that sine function is not one-to-one. Oh yeah, sorry, I forgot to mention, but six, I forgot to open it this morning. So you have chance to sign the attendance later after the class. I open it until 10. Okay. All right. If you have a sine x, for sure, sine x is not one-to-one, right? Because if you sine x real, okay, it's not one-to-one. It's not injective. Why? Because, well, f0 is equal to f of pi equal f 2 pi equals 0. So many things become 0. So it's not injective. It's not one-to-one. Okay. So the thing is, if it's not one-to-one, that's usually easy because you can restrict the domain so that it becomes one-to-one. Right, so let's see. The graph looks like, of course, you know the graph. It is periodic. Right, so 2 pi, 4 pi. Okay, now I have to restrict. Usually what we do here is restrict the f, the domain. That f is injective. Okay, so you have to find a domain so that f is injective. So injective is what? Injective in this case is monotone. So either increasing or decreasing. So how you choose the whether it is increasing or decrease, just only increasing or only decreasing, right? So one way is that, well, from 0 to pi over 2, that's increasing. Okay. So options. So we restrict to equal to 0 pi over 2. That's increasing. Okay, that's all right. Or from pi to pi over 2 to 3 pi over 2. Because that's decreasing. Okay, so or from 3 pi over 2 to this is a 5 pi over 2. So there are many options. Okay. And usually this one is not the option because this is not a large, this is larger. Okay. This is of length pi over 2. This is length pi. Okay, so you can still extend this to from pi over 2 to, let's see here. Okay, so that you have many options. Now it is a matter of choice. Okay, so what's the convenient thing? Okay, so we choose this one. Why we choose this one? Well, it is metric. Symmetric reason. Symmetric. Negative pi over 2 to 2 pi over 2. Okay. So then this is the what we have now. F, sorry, x, where x is injective. Okay. There we go. Therefore, it has inverse. Uh, so what does it mean? Uh, this is what we call the Arcus sign, or arc sine x. Arcus sign. Okay, so that's the inverse. And that's the meaning of the inverse of sine. Okay, so doesn't mean it is the inverse for the whole sine, but for sine only on our our choice, x between. Okay, therefore from the identity, right? So our sine now is between sine function, and this becomes from -1 to 1. Okay, and if you push that backward, this is what we call sine inverse. Okay, so if you have x and you have y. So an inverse identity means that if you start with x and apply sine, okay, and then you apply sine inverse to get x back, as long as x is between, okay, and if you start with y means that y is the number between -1 and 1, and apply sine inverse, arcus sine, and then apply again sine. So you sine inverse and sine will cancel as long as y between -1 and 1. Okay, so this is what we call the inverse identity. Okay, so let's see. Later we come back to this inverse identity. Or okay, just one example. What is the x of sine? Okay, how to compute that? Okay, we start with this. We let y equals sine inverse of x. Okay, so if you apply sine x both sides, of course, x is between. Okay, apply sine x both sides. So it's not sine x, but sine. Okay, sine of sine inverse x, because of the uh, the inverse identity, x between negative pi and pi over 2 and pi over 2. So this sine and sine inverse cancel. And we apply d over dx both sides. So this implicit differentiations, remember? From the second chapter 2, implicit differentiations. So derivative of x, that's the right-hand side, that's easy. It's 1. And sine y, derivative of sine is cosine. So this cosine y. And because of this is because of the chain rule, we have to multiply by y prime. Okay, so here y prime is 1 over cosine of y. Okay, it's still in y. How we express in term of x? Okay, so how we describe this? All right, let's see here. No, not from here. So you see that sine y is x. So in this case, we interpret as y is angle, x is a number. Okay, so you can draw the diagram. Okay, this is y, that's the angle. Okay, so it says the sine of this angle is x. Sine is the ratio between the opposite and adjacent. So this is x1. Represents x over 1. So this ratio. Right? And therefore, this must be, let's see, 1 minus x squared. Okay. So that's the cosine y is s over 1. So from here, the cosine is okay. All right, so let's see here. So it means cosine y is there. So this is so from here we get a formula saying that ddx is a number. Okay. There. Okay, so that's the trick of computing the derivative of inverse. Okay, questions? All right, so that's the general thing about the inverse. I mean, derivative of inverse function theorem. Okay, let's apply this idea to the Ln natural log functions. So let's go back to natural log functions. See, our Ln here is So, yes. Okay. So this is monotonically increasing. So in this case, and f prime here is, we call this 1 over x. Okay, that's why it is always positive or x positive. So it's increasing, and therefore, see that it's the inverse exists. Okay. Okay, so we know the inverse exists. So um, what is the inverse actually? Okay, so we call that the log x. This is log base 10. Okay, so for if y equals log x, then that means, and this is if and only if actually. So if y is log base 10 of x, that means x is 10 to the 10 to the y. Okay. All right, so the thing is how the inverse looks like. So this case is 10 to the 8. How looks like. All right, so that's easy because you see if this is y equal x, then this should be the mirror image, okay, of this graph. All right, so what's a mirror image? Let's put it in. Okay, this is 1, then this becomes this image. And because this asymptotic to negative y-axis, and the image should be asymptotic to negative x-axis. Okay, so that's the graph of the inverse. Okay, so it looks like a uh, well, exponential functions. Okay. Okay, so we say that this is the inverse of this is called exponential functions. So the green one. Okay, so the inverse of x from here, right, the inverse is of the exp. We call exponential functions. So for time being, we call it exp functions. Okay. So, so from this identity, y equal ln of x, okay, and apply exp x. Now because exp and ln are inverse, they cancel, right? So you get x. Okay? So that means this means x equals exp of okay. This is inverse identity. Okay, for example, we know the graph of exp. So that's the graph of okay. So inverse identity is exp of ln of x is this x, okay, and ln is for x positive, okay, and ln of exp that equals to also x for whatever exp must be positive. That's okay. So there's the our inverse identity. Okay, so the question is, what is compute the x of the exp, and what is the integral of the exp? Okay, so let's compute this way. Let y equal exp x. Okay, that means x equals ln of y. Okay. So if you take ddx on both sides, you get 1 on the hand side and the result of ln of y. Okay, because you use the chain rule to get 1 over y times. Okay, so that means y prime is let's see, it's the same thing. What is y? Y again is exp. Okay, so then we get this formula. dx of the exp of x is again exp. In fact, this is the only functions that doesn't change anything if you take derivative. Okay, so if you have polynomial, for example, if you take derivative, then the power reduced by 1. Okay, each time you take derivative, okay, but this functions now is, well, it doesn't change anything. It remains exp. Okay. Now, if the derivative doesn't change, remains the same, then the integral also Doesn't change anything. Okay. Okay. Let's see. Example now. So let's take derivative of x. Okay. So using chain rule, we get, well, it's still the same. EXP is still EXP, but you got to multiply by what's inside this derivative. Okay, so x plus cosine of x. Okay, so that's a derivative. Questions? Okay, so here use the substitutions. U equals x squared plus 5. Then du is just 2x dx. Right, so it's x dx. All right, so substitutions, this becomes 1/2 integral of, uh, this is just exp of u du, which will give you 1/2 exp of u. That's, or it is e. Okay, okay. All right, so let's see. Uh, the question is, um, check exp. All right, so e equals 1. Okay, so let's see here. Um, from actually we know for y equals, say, then x is expressed as 10. Okay. So we can, um, so how to get the 10? So to get the 10 is, let's see, um, this is base 10. Okay, how to get that 10? We get the 10 is that a y10, because log 10 is 1. Okay, so we call this base number. Base of logarithm if log, say, base a x is 1. This equals 1. So to find the base for the xp, how to find base for ln? Okay, you got to solve these equations. Equals 1. Because the base, if you get the solutions, that's the base. The solution is the base for this log functions. Okay. So we now try to find, let's do this one here. Okay, so let's ln, just punch in your calculator, for example, just checking ln of, for example, ln2, ln3, for example. So this one here. Okay, so I use the, remember the bisection method? Okay, so let's see here. If you plug in x equals 2, and you can check the g of x. G of x is 2, x equals 3. Okay, so let's check this one, minus 1. So if you plugged in 2, what you get there? Get the calculator. Okay, so ln of 2 minus 1. That's ln of 2. See, I need to 2 minus 1. All right, so that's negative 3, 1. So that's negative. And if you plug in 3, however, so ln 3, uh, that's 8, that's positive. Okay, so by what do you call it? Not mean value, but intermediate value theorem. Intermediate value theorem. There is x. X must be between 2 and 3, so that g of x equals 0. Okay, so there is a number which makes you this equals 0. Right? So you can check the use in bisection method. Okay, it's 2. This is 3. This is a 1 below. This is above 3. Okay, so you can check. Use 2.5, for example. Check 2.5. Again, let me just do this. And 2.5. Okay, minus 1. Get negative. That means this is still negative. So that means x must be somewhere here. Okay. Must be between 2 and 5 and 3. Okay, you keep doing these bisections. Bis, on bisection method, and you get something like x is 2.71. That is the what we call the Euler constant. And this is what we call the number E. Okay, so E is the solutions ln of x minus 1 equals 0. So E is the base of the logarithm. Okay, so now we know that the here we get that exp of x is nothing but e to the x. Okay. Okay. So here, so that's why we know this something that we are familiar with. E to the x plus. Okay. Questions? Right, so let's do one more example. This. So this one, letter E denotes unique positive real numbers such that ln of E equals 1. So number E turns out to be that's irrational. So this should be more than this one. All right, so this the exponent of r equals to e to the r. We can extend this to e to the x. All right, so this is what we get. Okay, and then the properties of those e to the x. E to the a plus b is gets e to the a over b, a minus b. That's a over minus. Okay, and e to the that's oh, e to the 0 is okay. So there's this. Yeah, first one. Derivative, we talk about the derivative when e to the x. Okay, let's find this. E to the x squared ln of x. An example. E to the x squared ln of x, for example. Okay, so then we have this the derivative. Exponential remain exponential. Okay, but because you have chain rule, then uh, you get to multiply by the derivative of the x squared ln of x. Okay, so to use the product rule, so to x ln of x plus x squared, derivative for ln of x is 1 over x. So it's 1, right? So this is the derivative. Okay, I guess we'll stop here. We'll continue next time with the how we define the uh, general exponential and log functions in the more general. Okay, so 6 4. Let's see. Yeah, general exponential and logarithmic functions, and then the okay, differential equations. Okay, questions?
Sir, I want to ask about the attendance.
Yes, I will open this now after I close this. Okay. I'll open until 10. All right.
All right, thank you, sir.
Okay, if there's no questions, I'll stop the session here. Stop the share and then stop the record.